So this lecture, I'm just going to preface a lot of Chapter 4 with some basic understandings. If you haven't done so already, go ahead and go to the helpful information sheets that are posted in that section for Chapter 4 and have handy a copy of both the solubility rules and the activity series, because we're going to be talking about that in this lecture. So when we talk about chemical reactions and chemicals, we can either have physical changes or chemical changes. We've talked a little bit about this already. But a physical change means you can change some composition of the compound without changing its actual characteristics. So for example, if I freeze water or boil water, it's still water, it's still H2O. I'm not doing anything to make it a different compound. In a chemical change, you can't get the original substance back. So, for example, if I burn wood, no matter what I do, I'm not going to get that charred wood back to the original wood state. If I have a car that is rusting, for example, that's oxidation, I can take the rust off and grind it away and repaint, but I can't ever turn that rust back into metal. So we're going to talk about technically there's 4, I like to call them 5, but most books will combine 2 of them. So there are evidences for chemical reactions. When a chemical reaction is actually occurring, you'll know it by a couple of different ways. First, there's either a gas produced, which we'll see by the way of bubbles. Another evidence of a chemical reaction is a solid is produced. Now, a solid in solution doesn't look like a solid. It's not like, throwing a piece of rock into water. That's not the kind of solid we're looking at. But when you have this distinct coloration and something that looks more dense than the liquid present, that's what we call a precipitate, and it is the solid that is formed. Another evidence is permanent color change. We see that here, where we have not only precipitate in the solution, but it's a distinct yellow color. It's some sulfur that's precipitated out. Sulfur is traditionally yellow. We can also see this color change with an acid-base reaction or a neutralization reaction when phenolphthalein is added to it, which is a color indicator to indicate the presence of hydroxides. That's going to become important when we talk about types of chemical reactions. And then this is the 4th one that I like to break these 2 up. Lots of books combine them. So they say 4, not 5, is heat or light is observed. In exothermic reactions, you will see that, or you will feel, or even maybe see light and heat. Sometimes in exothermic reactions, you can hold a test tube and you can feel that test tube getting warm. In the example of a firework, you can see the colors in the explosions. Endothermic reactions absorb heat, and heat goes into the reaction, into the system, in order to have whatever reaction is going to occur. And when I say heat in, I don't mean just as a catalyst, where, for example, if you think about boiling water and having, the heat put in, if I put my pot of water outside, eventually it would all evaporate. But by adding heat and boiling it, we're making that process just happen faster. So I'm not talking about that kind of heat. I'm talking about heat that goes into a reaction in order to break bonds. It is part of the chemical reaction. So generically, we can write chemical equations a certain way. So on the left-hand side of this generic equation, we have reactants. This is our reactant side. This is our product side. And the arrow means yields or produces. Okay? If there's going to be a catalyst, and sometimes it's not just a catalyst, but maybe something else that has to go into the reaction as kind of a secondary reactant or intermediate, we write those generically above or below the arrow. You'll mostly see anything outside of a catalyst above or below the arrow once you get into organic chemistry, if you have to take those courses. But in Gen Chem 1 and 2, what's above the arrow is generically just a catalyst. And remember, a catalyst just speeds up the reaction. It doesn't make a reaction go that wouldn't normally go. So another feature of writing chemical reactions are uses of telling us what state each compound is in, compound or element. We use G for gas, L for liquid, S for solid, AQ for an aqueous solution. And here's just some examples of symbols you could see. So again, the arrow here, it means produces or yields. Plus sign means add or act together. And actually, I want to go back really quickly. I want to make one thing very clear. So when you are looking at these chemical reactions, I want you to think of this plus sign as add together, just like in math. And I want you to think of this plus sign as and. Okay, so A added to B yields or gives us C and D. Okay, it's going to be very important. So back to this, you'll see here, just for example, this arrow, see they're a little bit different. All this arrow on the red arrow that I circled in red, it's got a triangle above it. The triangle is the universal symbol for heat, and in this case, it's a catalyst. Sometimes you'll see a metal as a catalyst, but what this is showing you here is that written above the arrow, if anything is written, it is our catalyst for these purposes. Also, I want to just mention that if a reaction is not going to occur, you're going to write the reactants, whatever they are. And if no reaction occurs, we'll talk about that in a few minutes, you just write NR. Okay? All right, so here's an example of a chemical equation, an actual one, not a generic one. So what we have here is we have acetic acid. You should know that because you're now starting to recognize this as acetate. The hydrogen goes out front. And so this is one of those acids where we drop the hydro and use the polyatomic, which is acetate, to derive the name. So it's acetate. If ate, then ick. If ite, then os. It's acetate. So this is acetic acid. And it is an aqueous solution. And then sodium, either hydrogen carbonate or bicarb, I would accept both terms, yields sodium acetate plus water plus carbon dioxide. Okay, so this particular type of chemical reaction, if you were to see this in a word problem, it would read something like aqueous acetic acid is added to solid sodium carbonate and yields aqueous sodium acetate, liquid water, and carbon dioxide. There's a typo here. This should say sodium hydrogen. Sorry, that's my sound on my cell phone. So sodium hydrogen carbonate, and it yields aqueous sodium acetate, et cetera, et cetera. So you can see why naming and being able to go between the name and the actual chemical formula is now critically important. If you can't see, for example, sodium acetate and write this, you need to go back and practice those worksheets. Going back and forth between the chemical formula and the name will be critically important to you doing well from here on out. So there are 6 different types of chemical reactions, or categories we're going to put them in. Just like we had the different categories of naming, we're going to have different categories of types of reactions. Those are combination, decomposition, single replacement, double replacement, neutralization, and combustion. Combustion we've talked about a lot already, so I'm just going to re-mention it again. We talked about it a lot when it had to do with balancing. So if you just recall that combustion reactions are always the same. You have some type of hydrocarbon, either with or without oxygen, that is added to oxygen in the presence of heat, and it always gives us carbon dioxide and water as the products. So generically, this is how we can represent these different types of reactions. Combination, A plus C gives us AZ. Decomposition, AZ decomposes back into A plus C. Single replacement, we have a single metal, and some sort of ionic compound. And if a reaction will occur, the single metal will replace the metal in the ionic compound. Okay. Double replacement, that's when our cations switcheroo and switch places. And then neutralization is always some acid plus base gives us a soluble salt and water. I want to remind you that when I'm dealing with neutralization reactions, that I will write water as HOH. You cannot input that by hand into your online homework. You actually have to write H2O. But on a piece of paper, writing it as HOH allows me to clearly see the hydroxides for the purposes of balancing. So a combination reaction is simply just like what it says. You're combining two things to get one thing. It is also called a synthesis reaction. I don't care which term you use. I will simultaneously flip-flop between them, between the combination and the synthesis. There are three types of combination reactions we're going to look at, and these are these right here. So the first one is a metal with oxygen. The reaction is always the same. You have some single metal as a solid added to oxygen gas in the presence of heat, which will always give you the metal oxide. So if we had, for example, solid magnesium added to oxygen gas, remember oxygen gas is one of those 7 diatoms. There is the 7 that make the shape of a 7 on the periodic table, starting with nitrogen. So the diatoms are nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. They all take on that symbol subscript 2 in their free state, meaning they're not bonded to anything and they're not an ion. And oh, don't forget about hydrogen. So there are 7 of them that make the shape of a 7 on the periodic table. Don't forget, because if it says oxygen gas, you know it's a diatomic in its free state, in that O2 form. So you'll get, in the end, magnesium oxide. Why do we get magnesium oxide? Because when magnesium becomes an ion, and this oxygen gas here splits, they become ions also. Okay. And I'm writing 2 magnesiums because there are 2 of them. That's what the balancing tells me. So what will happen is these, oh, I don't know what just happened there. Hold on. These will come together and form in a 1-to-1 ratio. And these will come together and form in a 1-to-1 ratio, giving us 2 magnesium oxides. I want you also to remember that when we write these chemical reactions, that we're just writing one representation of one of these happening, when really in a container they're surrounded by billions. So the second type of synthesis is a non-metal plus oxygen gas, and will always give us a non-metal oxide. Now, for the purposes of this course, I don't ever expect you to be able to predict what the final non-metal oxide would be. It can be many different things, okay? I would have to give you that information. I also want to make it very clear that it is not O2 over here because it's O2 here. That has absolutely 0 correlation. Okay, and again, for this course, you don't have to worry too much about understanding why it is what it is. A potential product could have been S2O2. It could have been SO. It could have been S3O2. I mean, this last one I totally made up. But I'm just saying there could be a number of different possibilities that the non-metal oxide could be. So just know you would have to be given enough information to know what the product is going to be. Then finally, there are a metal and a non-metal in a combination reaction. So a single metal and a non-metal will come together to form an ionic compound. So an example of this could be lithium bromide. Lithium bromide in the presence of heat will give us a lithium bromide solid. Okay, so solid lithium and bromine gas in the presence of heat will give us lithium bromide. That's just two things coming together to form one. You're going to have to go back and remember your charges and what happens when things become charged to figure out how they will come together. The decomposition reactions is just like what it sounds. Something that was a compound will decompose into its individual elements. So for example here, you have to be told mercury 2 oxide. Here we go, mercury 2 oxide, and it decomposes into mercury and oxygen gas. I want to clarify something that I haven't said up to this point. For mercury, we can have Hg2 plus or Hg2 2 plus. This format right here is actually the +1 form, or the mercury 1 form of mercury. So when we have decompositions, we can have metal hydrogen carbonate decompositions. So always the rule, when you have a metal hydrogen carbonate and it decomposes, you will always get as a product the metal carbonate, water, and carbon dioxide. Those are always the products. Whatever this metal is, it will always be the metal carbonate, water, and carbon dioxide. This nickel carbonate could continue to decompose, and if it does decompose, here's just another metal carbonate. Okay, it doesn't really matter what it is. If the metal carbonate continues to decompose, you're going to get the metal oxide and carbon dioxide always as the products. And then like we saw back here, once we have this metal oxide, it can continue to decompose into its individual elements. So I can go from a metal hydrogen carbonate, which decomposes into the metal carbonate, water, and carbon dioxide, always are the products. Then that metal carbonate can continue to decompose into a metal oxide and carbon dioxide. Those are always the two products. And then that metal oxide can continue to decompose further into its metal and oxygen gas. So the activity series, this is where you need to pull out your activity series. If you don't have it pulled out, please pause the video and go grab it and have it handy. Your activity series is what you use to know if a single replacement reaction is going to occur. Will a reaction occur with the single metal and the ionic compound we have? So we use the activity series with single replacement, and we're going to be using the solubility rules for double displacement. We'll get to that in a minute. So here's your activity series. And what this means is, bottom to top, you have increasing ease of oxidation. What does that mean? It means the higher up the chart, the easier it is for that metal to oxidize, to form an ion, and to kick something else off. So what in the world do I mean by that? Well, if I had, for example, copper, solid copper, and I added it to nickel to nitrate, the question is, would a reaction occur? Well, copper is found right here, and nickel is found right here. So what this means is, because copper is lower on the activity series, it is not strong enough to come in and kick off that nitrogen. It's not strong enough to do that. So we will get no reaction. However, if I had the reverse, if I had solid nickel and copper 2 nitrate, what I would see is that nickel, because it's higher on the chart, it is reactive enough or strong enough to kick off that copper. And what I would get as a final product would be nickel 2 nitrate plus solid copper. The copper would precipitate out. Those would be my products. So I look at the activity series to see if my single metal is higher on the chart than the metal involved in the ionic compound. Okay, is the single metal higher, therefore more energy, than the metal involved in the ionic compound? If the answer is yes, a reaction will occur, and that single metal will come in and kick off the metal in the ionic compound, and then the metal that was in the ionic compound will precipitate out as a solid. So here's another example. If we look here and we look at our activity series, we can see again that copper pretty low on the activity series, and iron is pretty high up there comparatively. Okay, so if we look again, here's copper, here's iron. Okay, iron is much higher up there. So what this means is iron is much stronger and much more reactive than copper. So it will easily come in and kick off the copper, forming a new ionic compound that will be aqueous solution and a copper solid that will precipitate out. Sometimes when you have an acid, and when we see these acids here, we're going to be looking at the hydrogen that is on the activity series. And again, if you go back and look, you can see hydrogen is just above copper. Okay, so the question is, now is the metal higher than the hydrogen on the chart? If the metal is higher than the hydrogen on the chart, then it will go ahead and react, and it'll kick off the hydrogen, but this time hydrogen will not precipitate out as a solid. It will reform into its free state, into its diatomic form as a gas, and this is where we get bubbles. Okay, you would see bubbles forming if this is going to react. Metals that are less active than hydrogen, meaning lower than hydrogen on the activity series, will get no reaction. By the way, this right here, this is the reason that jewelers use acids to test to see if gold is real. So like if you want to sell some scrap gold, you know, maybe you have some broken chains or one earring or what have you, and a lot of people will take them to the jewelers where they can sell their gold. The first thing the jewelers will do is take an acid and apply it to the gold. If there's no reaction, they know it's real gold. If there is a reaction, they know it might be, oh, I don't know, maybe an alloy or fake gold, maybe just plated gold. And so that's why they do this. Literally, chemistry is everywhere. So when we get, just keep in mind, when we get either water, which can behave as both an acid or neutral, it can also behave as a base. When we have anything with a hydrogen out front, anything at all, if the metal involved is higher on the list of the activity series than hydrogen, then it will react to form a new compound, and the hydrogen will get kicked off as a gas. I want to remind you, this 2 here has nothing to do with that 2 there. It is not a 2 on the right-hand side because it was on the left-hand side. You have to go back and remember that water is really HOH. And so if I'm looking at sodium, the sodium's going to come in, kick off that hydrogen, and it'll form NaOH. But remember, plus H2, remember, we're only writing one representation of this. There are quadrillions of these happening simultaneously. So easily there's another sodium atom and water molecule there that are going through the same process in order to get this H2 formed. All right, solubility rules. So we said the activity series we use for single replacement. Solubility rules we use for double displacement or double replacement. Okay, so what this means here is we're going to go through these and look at them, and you have to know these. You don't have to memorize these, but you have to become familiar with them. I will let you use these on your test, but you just have to become familiar with them. So the general rules are, in this first group here, alkali metal ions and the ammonium ion, for example, lithium, sodium, potassium, and ammonium, those are all soluble in water with no exceptions. So anything that they're bonded to, as soon as you add water to them, they will all break apart into their individual ions. Acetate and nitrate ions, they are always soluble, no exceptions. Halides, group 17s, chloride, bromide, iodine, etc. These are generally soluble unless they are bonded to a silver, mercury, or lead. Then they become insoluble. Sulfate ions, again, generally soluble unless they are bonded to a strontium, barium, or lead. Then they become insoluble. Okay. Now the ones that are generally insoluble are the carbonate, chromate, phosphate, sulfide, and hydroxide ions. All of them have a Rule 1 exception. So if any of these are bonded to anything in Rule 1, they become soluble. Sulfide and hydroxide ions are all Rule 1 exceptions. So if they're bonded to anything in Rule 1, they'll be soluble. Or if they're bonded to calcium, strontium, or barium. So calcium, strontium, or barium, or Rule 1, then they are soluble. If it's anything except those, it's insoluble. So for example, sodium hydroxide is soluble. Magnesium hydroxide is an insoluble solid. So a double replacement means that the cations switcheroo. They swap places with anions. So you'll see here, A was with X. Well, there's A and there's X. B is with Z. Once it's reacted, there are your B and your Z's. Okay. Now, in order for us to say a double displacement reaction has occurred, one of the products must be a solid. Just one of them. There must be at least one solid formed. If no precipitate is formed, there is no reaction, and we simply say NR. So how do we figure it out? Well, what I always like to do is say, okay, I'm going to always pretend as if the reaction did occur. Then I'm going to go to my solubility rules and see if a solid formed. Okay, so here are my reactants, and I look at my solubility rules and I say, okay, when I look at chloride here, that is my halide ion rule. They are always soluble, the halides are always soluble unless they're bonded to a silver, mercury, or lead. Barium is not a silver, mercury, or lead. Therefore, barium chloride is a soluble solution. Then I have potassium chromate. Okay, chromate is usually in my insoluble section. So I'm looking at this going, oh, that's normally my insoluble, but it has a Rule 1 exception. And the Rule 1 exception is lithium, sodium, potassium, and ammonium. Well, K is potassium, so that makes this chromate compound soluble. So this is also soluble. This becomes important because what that means is in solution, these are all broken up into their individual ions just kind of floating around. And that's how they bump into each other to form the new compounds and switch cations. Okay, so now I'm going to pretend like the switcheroo happened. So I write my products out as if it's happened. And then I say, okay, chromate. Now I got to go back to my list again. Typically insoluble. See Rule 1 exceptions. Barium is not a Rule 1 exception. Therefore, barium chromate is an insoluble solid. KCl. All right. Cl, that's a halide. Oh, potassium is not silver, mercury, or lead. Therefore, this is soluble, a soluble salt. Any ionic compound is a salt. If it's aqueous, then it's a soluble salt. If it's a solid, then it's an insoluble solid salt. Neutralization reactions mean acid plus base yields salt plus water. So we can recognize our acid because it is preceded with an X. I just said X, sorry, with an H. And we can recognize our base for the purposes of this as having that hydroxide. You also need to know that NH3 will also be worked with in this section as a base. And we will get the cation from the base and the anion from the acid to form our soluble salt. And then we will always form water. So for example, H2SO4 plus 2KOH will give us, here's our cation from the base, our anion from the acid coming together to form our soluble salt. And then we have the hydrogen. Hold on. We have the hydrogen from the acid and the hydroxide of the base coming together to form water. Okay, now I'm going to make a statement and I'm not going to give you the answer to this. Okay, just know you might see this as a bonus on a test. Just putting it out there. Okay, all neutralization reactions are double displacement, but not all double displacement reactions are neutralization. Why? I'm going to say it one more time. All neutralization reactions are double displacement, but not all double displacement reactions are neutralization reactions. Why? Think about that. That's it for this lecture. I'm going to add another section in a few minutes about electrolytes, and we'll talk about those in terms of strong and weak electrolytes, acids and bases, strong acids, strong bases, weak acids, weak bases, etc. If you have any questions, feel free to contact me.